Microphone on. It's recording. Okay, I'll trust it. So, anytime I lecture, whether it's in lecture, obviously, or in here, I try to record it and post it later. So we'll see if all this is going to work for us. Okay. So, this is our lab. This phrase, metathesis or metathesis reactions, it goes beyond the experiments that you see here, the reactions you see here. This is a broader concept. But for our class, it's really focused on what you learned in 151 called double replacement or double displacement reactions. And like, for example, when, you can see it right here between the silver nitrate and the sodium chloride. Right, in a double replacement reaction, the cation of one of the salts will bind up with the anion of the other, forming a new product, and then vice versa for the other set. Just a double swap, okay? So when you think of metathesis, think that, all right? Again, it is a broader category, and we're just focused on these few examples here. Now, I'm going to come back to this in a few minutes, okay? But there's actually, this is dealing with section, there it is, 4.2 in the, it's these precipitation reactions. Primarily, there's some acid-base reactions going on here, but there's only 3 that are acid-base reactions. All the other ones are precipitation. So let's take a look at that just for a little bit. And not that, right there. Okay. So first off, let's just look at the diagram here. These reactions are real simple, so I'm not going to demo it or anything. You'll see, basically what you're doing is you're taking 2 mixtures together, and they look like water. They're actually aqueous solutions, right? So you'd say these are clear and colorless solutions, all right? And what you see in these clear, or what we know about these clear and color solutions is that the cation and the anions are just free floating in those solutions, okay? So they're not bound up together. There's no solid sitting in there. Now, as a little side note, there's a solubility limit on everything. If you put enough potassium iodine, it will start forming solid in there, but that's not what we're talking about. Okay, we're talking about lower concentrations. It dissolves very easily. And then when you combine those two, then you get this new product being formed. And it's pretty clear that something is happening here, right? You're forming a yellow solid. And that is just a simple precipitation reaction. And those are the kind of things that you'll see today. Sometimes the powder is white, sometimes it's yellow, sometimes it's blah, blah, blue, whatever. Okay, it just can vary. Now, when we say that a precipitant has occurred, sometimes you see, that kind of obvious separation between the solid and the aqueous phase, but you don't have to have that clear of a change. What we say is that really any degree of cloudiness in the solution is going to count as a solid, as a precipitant forming in that solution. So some of these, they may be a little bit faint, but again, if new solid is formed, no matter to what small extent, then we're going to count it as a precipitation reaction. And for those precipitation reactions, then what we want to do is we want to create a set of equations to describe what's happening in that solution. And how do we do an equation? Well, it's simple as, right, we have reactants, arrow going to products, all right? So in my reactants for the 2 solutions, we have the potassium iodide and we have the lead 2 nitrate would be the proper name for that. And let me just get the molecular formulas down here on the reactant side. So there is the potassium iodine, and then the lead nitrate would be written in this fashion there, with a 2 as a subscript on the outside of the NO3 polyatomic formula. Now, there's a way that we designate these aqueous solutions, and that is by using an AQ as a subscript here. So anytime you have these, where the ions are just free floating, it's an aqueous solution. I guess I gotta be a little more specific. Water is the solvent for those examples. Water is going to be our solvent for everything. I can't think of an example where water is not our solvent. Okay, so that's the other thing I guess that I should be careful with.
Have a different solvent, what would you use for the subscript?
You know what? I'm not sure, to tell you the truth. I don't think you would use AQ. You may understand, like within that particular example, within the context of the experiment, you may just know that the salt is dissolved in ethanol or something like that. Honestly, I can't recall the notation for like an example if an alcohol is the solvent. But this one is water solvent. And again, that's going to occupy most of our time in this class. Now, I said this is a double replacement reaction. Okay, so what's going to happen is that the cation of one is going to pair up with the anion of the other. And I'm going to form, that formula is KNO3. And then the anion of the first one, and then pair up with the cation of the second one. And then that correct formula is going to be PbI2. Right. Now, there's something important here to make note of. And you may be like, what's going on? Because there's a 2 as a subscript for the nitrate there, but then I only have 1 as a subscript for the nitrate there. And that's fine, because the salt formulas, which is what I'm writing here, these ionic compound formulas, they are dictated by the particular charges on the ions here. So let's look at that. Oops. Yesterday I mentioned that knowing some nomenclature is useful, and yes, that's true, but when you learn nomenclature, you learn this as well. You learn how to put ions together to form the proper ionic formula. And that's really more important than just straight up nomenclature. Because what we see for these ionic substances is that nature, they adjust the ratio between the cation and the anion so that the charges cancel out each other. So why did I do a 1-to-1 ratio here between the potassium and the iodine? Well, that was the simplest ratio that I could bring these two together, so that +1, grab your calculator. 1 + 1 - 1 equals 0. You're always after that 0 overall charge for the salt formula. Why do I have 2 here? Well, because if I have 2 nitrates, then I have an overall -2 charge, and that cancels out with the +2 charge on the original cation. Going to the other side, why do I have a 1-to-1 ratio there? Well, because the potassium has a +1 and a nitrate has a -1. So that's the simplest ratio that I need to cancel each other out. Now, a lot of times you'll see things like this. When you have 2 ions and you're looking at it and you're trying to figure out the ratio, well, notice the pattern here is that the charge on one indicates how many of the other thing I have, in this case the anion, and then the charge on the anion tells me how many of the cations I use. That's essentially, it's just a pattern that exhibits itself when you have these, non-equal charges showing up in the with the cation and anion.
Factory, just reduce it.
I'm sorry, say again?
And then if they have a common factory, you reduce it
Yeah.
to the lowest terms.
Yeah, so something like calcium sulfide. Instead of saying like Ca2S2, it's just like, it's like lowest common multiple. Is that what I'm looking for, maybe? And it's just Yeah, CAS. You'd use a 1-to-1 ratio there. Okay. I will do this again in class, by the way. I have a whole slide just on molecular versus ionic compounds. Yep.
So looking ahead in the lab, the molecular equation that's the molecular equation with the aqueous and the solid.
Yeah, good. Yeah. So this is going to be called the molecular equation, and we'll see that in lab in just a few minutes.
Although, would you want to balance it with coefficients or like not in this case?
You would.
Okay.
Yeah. Yeah. So this guy, you would then go in and you'd want to balance this. And, you know, there's some different rules for, or not rules, yeah, rules for balancing, like keeping, you know, balance of polyatomics as a unit, right? Nitrate, 1 nitrate versus 2 nitrates, whatever. For these metathesis, these double replacement reactions, yeah, you do that. So when I just look for the first thing I notice that's out of whack, and it's the nitrates, the first thing I notice, and I just start adjusting the coefficients. So I got 2 nitrates on that side, I got 1 nitrate on that side. Okay, so I'm going to add a 2 in front. What does that do? Well, it now affects the potassium. I have 2 potassiums there, and I only have 1 potassium there. So now I go back and I want to say, okay, let's adjust the number of potassiums to get it balanced out. And then lo and behold, what happens? You also balance out the iodine. Okay, so that's fairly typical for these double replacement reactions. Usually by 2 or 3 steps at most, it should be balanced. I always say that if you're on step 6, 7 and erasing and going back and forth, what's happened is that you've messed up on the ratio between the cation and the anion. Okay, so just if the balancing act hasn't wrapped up very quickly, check your ratio and make sure that your salt formulas are correct. Now, as it turns out, I'm still not done with this. It's balanced, the formulas are fine, but notice I don't have subscripts for the products there. And so what I have to do in this example, since I see that a solid is forming, I have to identify, well, which one of these is a solid and which one of them is actually floating around in solution. And I can, you know, I can look at that if I want to. Usually you don't have that information. Instead, you have something called a solubility table. Now, for this class, you can have it. I'll go into more details with this later on, but the tests are essentially open notes. You can have 2 pages of notes, okay? And so usually students rewrite the solubility rules. So your job is not necessarily memorizing the solubility rules, but knowing how to use the solubility rules. So let's take a look at that real quick. Now, if I'm looking for, well, let me just point out, so there's 2 different tables, okay? There's one that's dealing with common soluble ions, and that's, you're always looking at the left-hand side of the table. And then the other one is dealing with common insoluble ions. And again, it's the left side of the table that you're looking at. It's almost like you're reading a statement, you know. Insoluble ionic compounds contain sulfate except for when they form salts with these guys. That's kind of what the gist is for these tables. But the reason why I'm focusing this side and that side, you're primarily looking at anions, things with a negative charge. So if I look at my anions up here, it's really nitrate and iodine is where I want to start. So if I go looking for nitrate, I find it in that first table. Nitrate's there. And what it's saying here is that most compounds with, and I'm just sort of going step by step, literally, most compounds of nitrate are going to be soluble except for what? None, right? What that's saying is that there are no exceptions here. Nitrate Nitrate is always soluble.
Always?
Always. There's one obscure salt that I'm familiar with that forms a very slight insoluble salt, but you'll never see it. The guy that taught me this, he was 65 and retired in 94. And so, I don't know, he learned his chemistry in the 40s, who knows. And the guy that taught him probably earned his doctorate in the late 1800s, who knows. So I know a few little obscure things just because of, my chemistry heritage, if you will. And it's some weird salt. I can't even remember. I'd have to pull out my old lab book to even tell you. So that's why this is simplified. It's just like basically every nitrate salt is soluble. Well, I don't have to go any farther here. I mean, I know that, okay, so based on that piece of data, I know that's aqueous. And then since I know a solid formed, I know that that's the only thing left. The lead to iodine has to be
You know
solid.
it's solid form just because of the image. Okay, so it's
Yeah.
not like there has to be an aqueous, and a solid at the end of the equation. You can't end with two aqueuses.
You could.
Yeah.
But then
Yeah.
also looking at the chart, if you look at the iodides, you see that lead is one of the exceptions.
Yep. Yep. So then if we go, now imagine I don't have the observation. And all I have is this guy. And I want to figure out, does a solid form? And if so, which one? In that case, I can't stop at just nitrate. Then I have to dig into the iodine as well. And so if I go to my tables and I look for iodine, I find it here. And it says, okay, most of the salts of iodine are going to be soluble except for those three. Lead iodide is in that list. And also silver iodine is in that list. This weird mercury, diatomic mercury thing, that's in the list.
Looks like a lot of 2+ metals tend to be exceptions.
Yeah, there's definitely some patterns here. There's like this little cluster of calcium, strontium, and barium. They repeat itself over and over again. There's the silver, lead, or lead and mercury. There's the lead, there's silver, there's lead. Not silver. Mercury, there's silver. Anyway, yes, there's definitely some patterns going on here. And I'm actually going to erase all that because it's kind of messy. And again, our focus is how do we use the solubility table more so than memorizing this list? Because you can have these notes with you on the test and the final exam. Okay. Now, I'm going to pan down just for a second. I'm not going to do this problem. But here's a new one. Potassium chromate, and aluminum nitrate. In this example, notice I'm not told whether a solid is formed. I have to determine. Now, the fact that, this is a practice exercise, you can assume a solid forms, but, there's plenty of questions on the test, like, of the salts listed, which ones form the solid, or something like that, okay? So this is an example that I'll actually do in class, and I'll run through this whole spiel again in class, all right? So far, I've only done the molecular equation, and I'm actually not going to do, I'll talk about these and point them out, but I'm not going to, just for the sake of time and, it's enough of what we're doing here. I'm going to do the ionic equations in class, but you'll see some examples coming up. Okay, if there's no questions here, I'm going to jump back to the lab and actually point out a few things. Okay, so in this example that we were just looking at, with the silver nitrate and sodium chloride reacting, well, what did I say a few minutes ago? I said nitrate's always soluble, so I know that is aqueous and that is aqueous. Another ion that is in that list of always soluble, sodium. That's another one. Okay. Sorry. I try not to jump right around. But I do want to point out, like those three, sodium, potassium, nitrate, if you can remember that those three are always soluble, that could almost answer 80% of the questions associated precipitation reactions, okay? You know, depending on how the thing is phrased, blah, blah, blah. But when you do these labs, when you do these experiments, when you do these kind of questions, these three ions just show up all over the place. Because, right, when we set up this experiment and we go back to the stock room and we want to pull, the chemistry instructors, we want to pull a salt that we know is going to dissolve, we're going to look at sodium, potassium, and nitrate. That's just the easiest ones to pull off the shelf initially. Now, okay, so I got three that are definitely aqueous solutions. And then, well, we just talked about, if you look at the periodic table over there, we just talked about iodine. Well, iodine, bromine, and chlorine, and fluorine to some extent, they're cousins of each other. They're all halogens, and they all form very similar insoluble salts. And one of those is this insoluble salt with silver. And you can look back at that solubility table and, well, just
I
look.
just noticed hydrogen is in all the alcohols 17%.
Yes, so we'll actually address that, sort of, in just a few minutes. Yeah, it can, hydrogen is, it's the simplest element, and I like this periodic table a lot. It has hydrogen on both sides of the periodic table. Sometimes it acts as a cation, forming a +1 charge, and occasionally it'll act like an anion, forming a -1 charge. We usually see it with the +1 charge, and that's what we'll see in a few minutes when I do the acid-base stuff.
Speaking of the periodic table, like, I've always wondered, like, what's the proper ordering of group 3? Because sometimes you see it scandium, yttrium, lanthanum. Sometimes you see it scandium.
Oh. I try not to think about it. Yeah, because you got, what I do is I follow the numbers, 55, 50, 56, 57 in terms of reactivity, and then drop down to 58. But you're right. There's two different patterns there. Unfortunately, we don't have to worry about it. Those that are actually in that field and worry about those, they can take care of them. And then, there's the halogen group there, and they all form similar insoluble salts, which is where that silver chloride precipitant is coming from. Now, yeah, there we go, right? I called this the molecular equation. And I just want to sort of pan down, right? The introductory here is using that same reaction just multiple times and trying to illustrate all the different players here. So we have the ionic equation and we have the net ionic equation. Now let's just take a quick peek at what's happening. Again, I'm not going to focus too much on it here. I'll do those examples in class. But basically, in an ionic equation, you have all ions over there on the reactant side. It's showing us that, the reality is, right, because earlier we wrote that. And that's a true statement. I mean, with that notation, we know that water's a solvent and that it's an aqueous solution. We know that silver cation and the nitrate anion are independent and free-floating in the solution. Well, just to sort of go to the other extreme example, why not write out the equations independent of each other on the reactant side? That's the gist of the ionic equation. The only one that actually comes together is the one that actually forms the solid. Okay? So the only one that actually changes from the reactant side to the product side is the one that's showing the chemical change. And again, that chemical change is coming from this guy. Right? Those are the two forming the salt. Okay? And as it turns out, that's what we then focus on for the net ionic equation. So the net ionic equation is essentially, it's trying to give us the most important information, i.e. what is chemically changing in this reaction that we're looking at. Now, that leads us to one other little tidbit here. There is a phrase that we can use for the other two ions here, and that is spectator ions, and that is sodium and nitrate. They're just watching the reaction take place. They're unchanged from one side to the next, and that's one thing that the ionic equation tries to show. In some ways, maybe, it's more easy to show, okay, well, these are actually unchanged from one side to the next. They're not chemically changing. Why include them into the most important equation? Okay, great, fine. So know this, for chapter 4, for test 1, we do the whole shebang. We do molecular equation, we do the ionic equation, we do the net ionic equation. After test 1, once we get out of chapter 4, we're really primarily focused on the net ionic equation, okay? So we only have to deal with that beast. This lab in particular, you'll see. I mean, it just goes on forever, it feels like sometimes. Maybe that's just me grading and trying to keep track of all the pieces. I guess occasionally, we'll probably see the molecular equation someplace here and there, but just thinking about, like chapter 16, 15, it's really this guy, the net ionic equation that shows up over and over again. Okay, and so these different equations show up in their solubility table. They show up in our data sheet. So this is going to be associated with the experiments. Right? There's molecular equation, ionic equation, and the net ionic equation. Now, I'm not going to write out the full-blown ionic and net equations. I'll give you some, pieces of it, that kind of thing. I really just want to focus on the molecular equation and some of the things that's going on here. In particular, for the first 3. So one thing that happens here, for experiments A through C, these first 3, these are actually acid-base reactions. Chapter 4, we have a section talking about acids and bases. We'll get into all the details there. Okay, I don't want to do that today. I just want to give you enough to sort of make sense of sort of what you're seeing. And then it's D through, and I can't even remember this, L? D through L. The remaining reactions, those are the precipitation reactions. And I'll just go ahead and tell you, one reaction in that group does not react. For that one, you don't have to fill out any, you can just put no reaction over the whole shebang, okay, for that one, once you've identified. How do you identify it? Well, there's 2 ways. You can use the solubility tables and do the double replacement and say, oh, what's going on here? It actually looks a little weird. And say, okay, everything's still soluble. Or, right, when you do the experiment, you'll see no solid forming. That's the other way to do it. Let me erase that because there is a reaction for that one. Now, right here, I've already talked about precipitation reactions enough. I want to then talk about acid-base reactions. And they are still a form of double replacement reactions. There's a little twist on it, okay? So let's just look at this for a second. Let's just look at the first one. And you know what? First off, I want to write out 2 plus. I want to write out the ions that are floating around in the solution. Now, that first one, calcium carbonate, that is a traditional salt. It has a bona fide cation. It has a bona fide anion. And I just want to point out that, and this is something I'll go into more detail in class, but, where's calcium on the periodic table? It's that second family over. The elements in the second family, they form a +2 charge all the way down. +1 charge all the way down. Okay. Halogens, -1. Chalcogens, -2. The nitrogen family, -3, with some exceptions, but the first two, which are most important, -3. We have these periodic trends. Okay, so that gets us through most of these problems in terms of identifying the monoatomic ions. We'll deal with the transition metal group here in just a few minutes. Okay. Now, hydrochloric acid, HCl, that's a different beast. Okay, it's not an ionic substance. It's actually, oh, I don't want to do that. You can draw a Lewis structure for HCl. It has a bona fide covalent bond holding the hydrogen and the chlorine atom together. That's in the gas form. When it goes into solution, you don't have to all this, but this is a weak bond. And when it goes in solution, it actually breaks apart into these individual ions that are now free floating, right? Because we have the AQ tag that tells us it's free floating. And so that's where we're getting our cation and our anion for the hydrochloric acid. This particular feature that we see here of a weak bond and it breaks apart in water, that's what acids do. Okay? All the acids will produce some kind of proton in solution. Okay? And in class we'll talk about that in much more detail. Now, once we have that kind of out of the way, then we're just talking, it's a double replacement reaction. Okay? So I'll sort of just naively jump into it. Okay, great. So that's how everything's going to swap around. I'm going to do what is highlighted in yellow first, because that's a traditional salt. Calcium chloride. Now, remember chloride, it forms insoluble salts only with silver and mercury and lead. Where is lead? Lead. So calcium is going to form a soluble salt based on the solubility table. Okay, so I'm going to go ahead and throw in that AQ tag there. Now, and as it turns out, AQ, those ions are still free floating. Those are the spectator ions for this reaction. Let's just go ahead and fill that in. And this is something I'd like for you to do. Most students will just write in spectator ions below and then write in the two that are spectator ions. The other way to do it is you can, highlight or circle the spectator ions and just indicate those are spectator ions, whichever way you want to do it. But show me which are the spectator ions in each of the reactions that take place here, okay? Okay, so if that's the spectator ions, that means that the hydrogen and carbonate are what's actually going to react. And I'm actually going to put it up here and do it this way. So notice, right, I have a -2 and a +1. That means I have to adjust the numbers there. I need 2 of those protons to balance out the -2 on the carbonate. Okay? This is referred to as carbonic acid. I did not write it down here because this is an intermediate. This is not a stable molecule. What happens in these reactions is that the carbonic acid actually decomposes into water, which is a liquid, plus CO2, which bubbles off as a gas. So this is a classic vinegar and baking soda kind of reaction where you get the fizz, fizz, fizz. All right. Now, for the reaction that you're going to see, go ahead and do the reaction. I'm telling you what's going to happen. Do the reaction. It's real simple. There won't be a lot of fizz, fizz, fizz. There'll be a few bubbles that pop up. The concentration of that calcium carbonate is not terribly high, even though it is a saturated solution there, but it's still not too high. And so notice I don't write in carbonic acid here. Instead, I write down what I observe. Okay, so I'm going to water and CO2 down here. CO2 gas.
So, if you're producing water from the reaction, does that change the water level in the beaker, or is like the water that's being produced make up for the solvent that's being turned into gas or whatever?
It wouldn't be that noticeable. I think the volume probably doesn't change all that much, is my guess. Because it originally started as matter occupying space in this. That's my guess. The CO2 bubbling off, I mean, there could be a little bit of a drop, but
Technically lose a little bit of,
maybe a little bit. It definitely loses mass,
of course.
right? Yeah, for the CO2. How that affects the volume, I don't know. Question?
So then you would have to balance it.
Yeah. So then I won't do that here, but for all of these, right, go back in and just make sure
Should just be 2 HCl, right?
that everything is balanced.
Yeah.
Okay.
Okay.
Okay, so that's the molecular equation. Okay, I said I wasn't going to do the ionic and the net ionic, and that's still true. Okay, but let me just, I don't know. The net ionic equation is most important, right? That's dealing with the core features that are changing. That means water and carbon dioxide is going to be in the net ionic equation. Where do they come from? They came from those two. Spectator ions, they are omitted from the net ionic equation.
So you would just write CO3 plus H plus CO3 2 minus plus H plus gets you the H2O and CO2.
Yep.
And that's your net.
Yeah. Whereas the ionic equation, which again, after this test, no more. Right, you're writing in every single ion. You're putting in an AQ tag all the way across. Okay. But in the ionic equation, you still have water and CO2, right, as those formulas. Because that's what forms. And they're stable, and they are covalently bound molecular compounds. About the AQ tag, add AQ to all ions and soluble salts. So like, we add AQ there, AQ there. And then like for calcium, you want to add the AQ. If this lab feels tedious at some point, it is. Okay? That's one reason I say after this, we're not doing that ionic equation. It's not important after this. Okay? Experimentally, because I think I'm going to do this as a demo in class when the time comes, we're just going to skip B and C, and I'll explain a little bit why.
So we're not doing those today?
No, don't worry about them. They're really, you got to do a few extra things to really.
Do you want us to still write out the equation?
Yeah.
And stuff, but we're just not doing. Okay.
Yeah, skip the experiment. Complete the chart. Or what do you want to call this? Table, lines. Chart / equations. Like for example, like the evidence of the reaction, there's a pH change that's occurring for the first one. I mean, there's a pH change occurring for all three of the first ones. Anyway, the main thing, pH change is occurring for that first one, and then this gas.
Wouldn't the first one
Yeah, gas evolves.
Okay.
Yeah.
Real quick for the for A for the when you're writing the ionic equation in regards to the water and the CO2, is it water is like it's you do the Ca2 plus Cl minus plus H2O and then plus the CO2 so
Mhm.
you don't break those up.
Correct. Yeah. Yeah, so these molecular compounds, they'll stay just like they are.
And you said for C the evidence was gas evolution.
Yeah, and the reason why I'm saying skip it is that when a base reacts with an ammonium salt, and I'll go through the spiel here, it forms ammonia gas, but it doesn't form bubbles. Okay?
What?
If the concentration is high enough, you can smell the ammonia, but that doesn't work too well with our setup here. And there's another setup that's very sensitive to ammonia that I'll actually demo in the class. Do you have a question? Okay. So let's just do this one first, since I'm talking about it.
D or C?
I'm sorry, C. Okay, just like before, and maybe go just a little bit faster. Here are our ions. We do the double replacement. Okay. I'm going to do the easy one first. Those are the spectator ions. Again, sodium and nitrate are fairly boring. They just don't do much. Now, sodium metal's not boring. Sodium cation, very boring. Unless it's in the context of like high blood pressure, then it's not boring. Pretty much always a spectator ion. Now, since I'm calling this an acid-base reaction, anticipate, well, a solid's not going to form. Okay? This example maybe shows a little bit better. I don't know. But it's more characteristic of what we think of chemistry in the general sense of an acid-base reaction. There's a transfer of a proton somewhere in the solution. And that's how the proton is going to transfer in this reaction. I will go through acid-base reactions in more detail in class. Okay? But, that's going to dictate what our products are on the other side.
So do you get an NH3 and an H2O?
Yeah. So imagine, right, if I'm removing one H and one positive charge, what's left? NH3.
Is it still NH3 plus?
It's just NH3, yeah. Because the positive charge.
Oh, that positive is then
Yeah.
switched.
Yeah. When you see that H plus, it's literally a proton, that subatomic particle we know and love from Gen Chem 1.
And the
Right, just one thing, positive charge.
Is the NH3 still in solution with the
Actually, this is the gas.
oh.
Yeah. And this is one reason, again, the ammonia, it has a distinct smell, but it doesn't really bubble all that much, which is probably good because, ammonia, if you're dealing with a solution where ammonia is bubbling off, you're probably, you're not in this class. Ammonia gas is something you have to be careful with. And then the other side, if you got an H plus and an OH, right? The negative and positive cancel each other out, so overall charge is 0. And 2 hydrogens, 1 oxygen, it's water. And so that's our other product here. Oop. So one thing to note, water always has that L subscript. CO2 always has a G for gas. Ammonia, you probably won't see it all that often, to tell you the truth, but it would have a G as well for a gas. Everything else pretty much is, there'll be other things talked about with terms of gases and solids, but they're written out explicitly in terms of like you needing to know, oh God, what is that? most of the things that you'll label are going to be aqueous solutions. And then just a similar kind of, if we want to talk about net ionic equation, right? That's the chemistry that's happening. Sodium and nitrate don't change in this reaction. So if we're going to take these components of the molecular equation and write the net ionic equation, what we're talking about is ammonium and hydroxide. They change to ammonia and water. And that's what we would write in on the net ionic equation there. And again, I don't want to give you the answer, just sort of little pieces here and there. Now, in this example, same song and dance. These double replacement reactions are very repetitive. I mean, you're just doing the same. You're turning the wheel. It's the same thing over and over again. It's just that the outcome varies depending on whether is it an acid-base reaction, is it a precipitation reaction. But same kind of thing. We got the cation and the anion. Well, that's going to form. I'll just write it in. That's water. And then HCl or NaCl. That's it's just those are the spectator ions. It just forms a sodium chloride solution. So if you look at the products there, water, sodium chloride, there's no solid, there's no gas. To actually notice something happening in this reaction, you have to add something called an indicator to the solution that keeps track of the pH changes that are occurring in this process. And we'll actually, there's a decent chance that you've heard this information, right? pH of an acid is between 0 and 6. pH of a base is between 8 and 14. And then once you get a neutralized solution, that would be a pH of 7. So if we have an indicator, meaning this chemical compound we add to the reactants that changes color based on pH, then we can see like this would be red originally, this is purple originally, and then this solution would be yellowish green. Right? So we can see a color change due to that pH change. That would be related to the pH change. But again, I'm going to just mess with that in class when everyone's together. And just real quick, similar thing, right? That's what's changing. Those are only 3 things that get included in the net ionic equation. Questions, comments, concerns? Yes, please.
So for the lab data sheet, is that to be turned in after the experiment or with our lab post that question on Thursday?
Yeah, let's talk about that. So, so this will be due next Thursday, or early. You can submit it earlier, if you want to. And what's going to be due? Let's just go through it. This will be due, so the pre-lab questions for this one, all of those will be due. And I'll talk a little bit about the pre-lab questions just for a sec in a minute. And then this entire set of, A through L. Okay, this is the experimental side of things. And then for this one, it'll be all of the post-lab questions as well. And I'll talk about one of these also just a second. These down here, they're really addressing solubility table more than anything else. There's a CO2 comment. And some of these I'll talk about in class as well. So those are the pages you'll submit. Again, PDF is what we're wanting you to submit. And you can use the scanner on your printer at home. There's plenty of apps for phones and tablets that allow you to, basically take photos and then convert it into PDF, and then you would submit that through the link on Moodle for each of those labs. Yes? You're good? All right. Okay, let's talk about, I don't want to do this. I'm going to talk about this table. It says your observations. Yeah. I mean, you can go into the solubility table and just like cover this thing full of notes. That's not what we're wanting. We want you to look at the observations from this lab and then fill in this chart. And I'll address that in just a second. But first off, while we're talking about, let's look at the pre-lab questions real quick. On the number 2, it's only wanting the molecular equation. Okay, so it's just, you'll have 2 more things, and these.
So you don't have to do the plus, the minuses. It's just writing what
correct
in the end result.
Correct. Yeah, like this will be AgCl will be 1, and the other one is aluminum. Yeah. So you don't have to write out all the ions. And then you put the S and AQ tag where appropriate. The first 4 show up. Yeah, I think all of these form, if I remember my solubility, I think all of these form solids. Check the solubility table just to be sure, okay? And then on this one down at the bottom, notice you have this carbonate, and that's another acid there. Well. Those are the patterns that you're looking for when you form a CO2. Sorry, let me move that up. So this is analogous to reaction 1 that we looked at right there. So pretty much any carbonate salt with any acid will form CO2 in a reaction. And we'll talk about that reaction in class. That's one of the sections in chapter 4 that we deal with.
So you said N-carbonate salt
With an acid. Yep.
And for pre-lab number 1, I don't know if I can think of 5, maybe 4.
They're listed.
It's in the pre-lab.
Oh.
Yeah. And it'll be more than just what we're doing in this particular lab. Like I think temperature change is probably one of the things listed. The temperature changes occur in these, but they're so small that I don't know if a thermometer would even pick it up. Question number 3, notice that it is.
Also, doesn't the temperature technically change when a solvent dissolves something as well?
Yeah, and
So that doesn't even indicate a chemical reaction necessarily.
you could argue that is a chemical change because it's going from a solid state to now something that is an aqueous state, and heat change does observe. But you have a good point. Yeah, that's sort of on the borderline there in terms of a chemical reaction. And it really boils down to like intermolecular forces, ionic forces versus hydrogen bonds or ion dipole forces. That has different strengths from the react and the product side. But number 3, this is where you got to suffer and do the ionic equation and the net ionic equation. But it's just for that one there. You don't have to do it for all 5 of them. Okay?
Okay, so we just doing 2B.
Yeah.
We then write ionic
Yeah.
equation and
Yeah. So when it says, this is a little bit, illustrate basically what, write out the ionic and net ionic equations there. Right? What time is this lab? 1:40. We're fine. We got an hour. Let me do just one more thing. I promised this, so I'm going to do this. And I'm looking at letter D, reaction D there, with the ferric chloride reacting with sodium hydroxide. And the reason why I'm picking on this one is because it's going to illustrate what happens with these transition metals. So most transition metals, and then tin and lead, these post-transition metals here, those are the two most common ones to worry about. They can vary in charge. Brown and LeMay uses this term variant versus invariant ions. Invariant, they don't vary in charge. That would be the ones we've dealt with up to this point. Calcium's always +2, potassium's always +1. Those are invariant. Iron comes in at a +2 or a +3 charge. Copper has a +1, +2 are the most common. Even just knowing those, they'll help, but you still have to sort of dissect that formula to know whether you're looking at a +1 or a +3 charge. Now, one of the main clues is the 3 that's on the chloride there. Because one thing we saw is that we could switch those numbers around, meaning the subscript numbers in the formula, switch those to indicate the charge of the other compound. And that does work for this example. So what we're looking at is actually the ferric ion and then the chloride ion. Why are there 3 chloride ions? It's not just because of that rule. It's because nature has to balance those charges. Right? There's 3 of those, so that now there's a total of -3, and that negative charge can balance out the +3 charge on the iron. Nature prefers a low energy state. And when those charges are balanced in a salt formula, it's essentially a lower energy state. It just happens automatically. That's what it does. And so that's why we write it this way. Now, if you were given, let's do this. Cobalt sulfide, a little different, okay? One thing, so sulfide is in the chalcogen family. They're all -2.
So then you know cobalt's going to be a 2.
Yeah. So this is an example where that, like the just plain flip-flop rule doesn't work, because these charges are coming in at equal and opposite. Okay? So those are like the 2 variations that you have to worry about with these transition metal salts. Is it equal and opposite issue, like cobalt 2 sulfide, or is it not? So like the nomenclature videos on the 151 review. So I promised videos for 151, and I can't find the document, so I'm just making it up again. But the first 2 or 3 videos there will go into this topic about how to deal with ionic charges, blah, blah, blah. I don't want to say this is the most important topic of this semester, but it is a very important topic. It's not like, you're not going to get a lot of questions saying, what's the charge of this iron? It's not that. But you need to be able to do this type of analysis so that then you can answer other questions, such as what is the proper, right? Because if you write, that's incorrect, right? You have to know that this is a minus or +3 charge before any of the rest of the sequence makes sense in a way, or at least to get it right. You got it. Anyway, so just keep that in mind. Now, I will go ahead and tell you that, and you can do this experiment, like I said, all these are very simple. I mean, you're just putting in some drops of one with the drops of another, and it just reacts automatically. So I'm just going to tell you this, that the ferric hydroxide that forms is the solid. Okay? And the other thing, the sodium chloride, is the aqueous solution. You still need to balance, right? You still need to go back in. But the reason why I share this with you is because I want to fill in a little bit of that chart on the first question on the post lab. Okay? So these are my observations that I'm seeing in the experiment. That's what I want to stick with when I fill out this chart, which I mean that chart. And I'm focusing on the hydroxide for just a second. Okay, so based on that observation, I know that in terms of insoluble salts that I'm seeing, at least I know the ferric ion is going to form an insoluble salt. For what I've seen up to this point, in terms of soluble salts, there is one that we've dealt with a couple times now. That's soluble with sodium. And then I would write sodium in there. Does hydroxide interact other places? I can't remember. It might. It doesn't. Okay. So I'm actually filling out that entire thing. Some of these, and phosphate. I think phosphate and yeah. For the chart with phosphate and sulfate, even chloride, there's probably going to be multiple ions that you're going to write in here. But again, once you've done the experiments and you're filling out this chart, just use your observation from this lab, and just again go one step at a time. Ask yourself, well, have I seen any solids form with hydroxide? Yes. Have I seen any soluble salts with hydroxide? Yes. Nitrate. Well, we kind of already know none. Get back down there. None there. And I think at least one of the soluble salts that we see is sodium, but there's probably a bunch of others too.
So for carbonate, should we even mention the hydrogen cation?
Give me 1 second here. Notice that in F, the double replacement reaction sets up cobalt and nitrate. So based on my observations, cobalt is another one that would form a soluble salt. Okay, so scan your results to fill out this chart. I'm sorry, what was the question?
For carbonate, should we even mention the hydrogen cation?
You do not need to, because this is just dealing with precipitation reactions. Yeah, so these would be like observations from D through L.
Okay.
Yeah, we can be a little more. Oh, no, I don't want to say that either, though, because you can look at.
Just ignore gas evolution.
Yes, that's the better way to say it. Yeah. Yeah, ignore gas evolution. Because, the carbonate, calcium? Yeah, I think calcium was the one listed in that first one. Okay. That is pretty much what I did yesterday, so I'm going to stop there. Any questions, comments, requests? Okay. Let me do that so I'm over it.